So far, we talked about what it means for an infinite sequence of states to satisfy a formula. However, such sequences of states typically do not occur in isolation, but they form possible execution paths in a system, and the system can have multiple such execution paths. So next, we're going to discuss this more comprehensive system-based view. To this end, we define the notion of a labeled transition system, LTS for short. An LTS-M is a triple that consists of the following: a finite set of states S, a binary relation on S denoted by an arrow called the transition relation, and a labeling function between S and the power set of the set of atoms. As usual, a labeling function associates a set of atoms to each state. As before, these are interpreted as those atoms that are true at that state. And we also assume each state has at least one transition to another state coming out of it. In other words, there is no terminal state. In mathematical form, for all S1 in S, there exists an S2 in S such that S1 transits to S2. Now, given an LTS, we can define what it means for an infinite sequence of states to be a path in this LTS. It simply means that any two consecutive states in the sequence are connected by a transition. In mathematical form, for all numbers I, Si transits to Si plus 1, assuming pi consists of S0, S1, S2, and so on. To indicate that pi is a path, we usually show that there are transitions between its states, as seen here. So pi is written as S0, goes to S1, goes to S2, and so on. This is just a notation. Here is an example of an LTS. Remember the example from the introduction to model checking lecture, the one with two parallel processes that can request entering, can enter, and can exit a critical section. We model that by first choosing the following atoms, N1 and N2, to mean that process 1 and respectively process 2 is not in the critical section. So N means not in critical section. R1 and R2 to mean that process 1 and respectively process 2 is requesting to enter the critical section. So R means request to enter. And finally, C1 and C2 to mean that process 1 and respectively process 2 is in the critical section. So C means critical section. So I have a total of 6 atoms. 3 for actions by process 1 and 3 for actions by process 2. Now, here is the same system as the one from the introduction to model checking lecture, but defined as an LTS. It looks very similar, but now we're emphasizing the LTS components. There are 8 possible states, S0, S1 up to S7, with the shown transitions between them. Okay, so we show the actual graph, and with the labeling function shown in brown. This is a pictorial way to show an LTS. It, of course, corresponds to a mathematical definition of the components S, arrow, and L. The set of states S, as I said, consists of S0, S1 up to S7. And the transition relation consists of the pairs indicated here graphically. So S0, S1, S0, S5, S1, S2, S1, S3, S5, S3, and so on. S2, S5, S2, S0, S2, S4. So everything that is shown on this picture becomes a pair in this set. This is the usual way to define a relation or a graph as a set of pairs. And the labeling function L sends S0 to N1 and 2, S1 to R1 R2 to R1 and 2, S5 to N1 R2, S3 to R1 R2, and so on. In this example, the labels consist of each state is labeled by 2 atoms, but in general it does not need to be the case. So you can have any set of atoms from the available ones. Okay, so I hope that now you know how to switch between the picture of an LTS and its mathematical definition. and vice versa. Now, a good way to visualize the paths through an LTS, starting in a given state, say S0, is by mentally unwinding the LTS into an infinite tree as shown next. Let us consider this small LTS as an example. The tree obtained by unwinding it looks as follows. The root of the tree is S0. These branches into S1 and S2 because this is a situation into in the original LTS. So S0 transits to S1 and S0 transits to S2. We indicate here on the second level all the states to which S0 goes. And then on the third level, we indicate all the states to which the level 2 states go. So S1 transits to S0 and to S2, as seen here. S1 transits to S0 and to S2. So this is reflected in the tree. On the other hand, S2 only transits to itself in the original system. So we see that on the tree, S2 moves forward into itself. And so on. So we have an infinite tree here. The paths through the LTS are exactly the ones through its unwinding tree. In fact, the unwinding tree is essentially the LTS projected forwardly, with the paths depicted more explicitly. So let us see what are the possible paths starting at S0 in this LTS. Some people prefer to depict them directly on the original LTS, others prefer to use its unwinding tree. You'll do what feels more intuitive for you. Let's depict them on the unwinding tree. We have two cases of what can happen on a journey from the root S0. We can either keep moving left, in which case we have S0, S1, S0, S1, and so on infinitely, which gives a path that we can indicate like this in mathematical notation. So S0 goes to S1, repeated an infinite number of times. In other words, concatenated with itself infinitely. A second case is if at some point, so we go left, and at some point we veer right. And then we would be essentially looping in the state S2 as soon as we veer right. This has two subcases. If we veer right when we are in S1, let's say here or here, then we are going to get into a situation like this. We have S0, S1 n times, and then S2 infinitely. Or if we veer right when we are in S0, either here or here, we get into this situation, S0, S1 repeated a finite number of times, followed by S0, followed by the S2 loop. And these cover all the possibilities. Of course, we could also see all these possibilities on the original LTS, not only on the tree, if we were willing to follow path back and forth on this graph. The three cases are S0, S1 infinitely, or S0, S1 finitely followed by S2 infinitely, or S0, S1 finitely back to S0, then S2 infinitely. Okay, I hope that now you have a good intuition of what a path is.